Hi everyone, my name is Carolina, and I'm from Minas, Portugal. Today I'm going to talk to you about a little bit analysis of exploration data to monitor the condition of stamping press. So this work came from a project I cannot where we are developing a, a new stamping press. But our task is not the manufacturing from the manufacturers. We have the goal to build a kind of digital twin for the press. This digital twin has two components, a multi-body model of the press, and then a monitoring condition system that will use data from sensors that are on the breast to monitor the condition of the breast. And in the future, we'll use that data to feed the multi-body model so that we can have a digital model that is very approximate to the reality of the breast. But the focus on this work is the monitoring system. Uh, and the goal of this system is to detect and identify potential failures of the breast so that we can take measures and to avoid these failures. To design this monitoring system, we had to begin to define what data we would collect and where from. These data had to be related to the failures that we want to detect. So we had to research what kind of common failures the stamping press has and what data would we collect to identify them. So we get to this conclusion. The stamping press on the slider crankshaft system, we chose to measure the temperature of the oil to monitor the lubricant regime and also monitor acceleration from bearings and the shafts. Then the tool that is a very important component of the brace and is in direct contact with the process. We chose to monitor the loads that are being applied. And from that, we can monitor the process, the press condition, and possibly, if energy is being dissipated and get a more efficient and energy efficient system. Then from the slide and the frame, there are structural components that are connecting all these the other components. We thought of having a measuring acceleration. And then since this press is servo motorized and we have a servo driver, we can also use the motor data to monitor the condition of the other components. But as I said in the beginning, we will talk about the monitoring, the acceleration monitoring or the vibration monitor. What we thought about on this, it was to use the acceleration to mainly monitor the structural condition of those components, and this is this is the methodology that we think. So we have the data. We will extract time features that are that can represent the behavior of the signal, and with operating limits, so limits that above the price is not in a good condition. We compare those features to those limits, and if the features are above those limits, the price is in no good condition and an alert is sent. In parallel, we have a model analysis where we are going to get the modes that are being excited during operation and by also monitoring the frequencies and magnitudes. If they change from what we expected, we know that something is different in the integrity of the structure, because we know that if the stiffness of the mass or the geometry of the structure changes, the modes that are being excited, especially the frequencies changes too. So if we uh, detect a change, a brutal change on the frequencies, we know that something is also wrong. So time features, as I said, they represent the signal. This is a good method to analyze the data, because it's much more easier computationally, because we are representing a signal with thousands of points of raw data in like 10 points of data, 10 features. And we know that they represent what the signal is giving. Then on the model analysis, since we do not know what is being excited, the input expectations on the breast, we have to use operational model analysis. And with that, we only need the data that we are acquiring to get the modes that are being excited. Here, that we tested two methods, one time-based, the stochastic subspace identification, and one in the frequency domain, the frequency domain decomposition. So now I'm going, so now we have the methodology. Now we need data to test the methodology to see if it is right. So what we did was we took a press. It's different from the one that is being developed, but is a new press in health condition, and we use some accelerometers, and we get data from this press that has the same main components as our press, the slide, the frame and bearings, and we use three loading conditions and obtain data from that. The loading conditions, so we had no load at all, so we had the slide go up and down and have no 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 block. Then we had load conditions where the slide would go up and down and contact with this metal block. And then we did overloads to simulate a failure where the slide would have to go above beyond the surface of the block, so it has like a resistance. And when it wanted to go further, it couldn't, and the press would go overload and stop. So now the data that we've collected. I'll show you just one example. There's missing a graph, I don't know why. Okay. So we took acceleration from the slide. That's the example we're going to use today. This to show in the y-axis we have is the direction of the movement of the slide. So we can clearly see the movement, and in this case it was in load conditions, so we can see the impact with the block. And then the x-axis and the z-axis are the perpendicular ones. So what we see is like this damping effect, which is the response of the material to the impact. She's very curious. So we took this data, and now we're going to show you what we get in terms of time features. These are some examples. I don't know. These are some examples of some of the features that we are extracting. We computed those, obtained those reference limits on the red and yellow by using the data, the average value, and using the standard deviation and we get some reference. In the loading condition, there might be an alert or two, but it is in good condition. Then if we go to the no load, we see that the values are very low and far away from the reference one. And then when we see the overload, we actually see a spike and over the limits that would be expected. So we know that probably these time features are really representative of the different operating conditions, and from that we can actually monitor the process and the condition of the bus. Then for the model analysis on the loading condition. So here we have in the SI method, I'm presenting you the power expecting density. So we have the signal decomposed by its frequency components in the three axes. As you can see, it's very noisy. So I applied filters, but it needs more filtering. And above it, we have the stability diamond that's the result of the SSI method. And from that, we have the stable modes that are the modes that are identified by the method. And what we would see is on these red lines that there must have been some spikes on the bar spectrum, but since it is very noisy, we cannot clearly see that. And then on the frequency domain decomposition, what we are seeing is the per singular value of the decomposition of the power spectrum. And similarly to what we would expect on the SSI method, we would see like a spike, and then this would be a mode, an excited mode, but this data is a little bit noisy. But if we look at the first modes that are identified by one another, 3 hertz, 1 hertz is a little bit similar, the 8, 9 hertz. So maybe with the 47, 48 hertz, maybe we are seeing some modes here. Then if we see the no loads, here we actually have a problem that I included in this to a fun fact. We one of the axes stopped measuring, so what we see on that green signal is like noise, just noise. And when we see the power spectrum, which is the orange line there, we can see some spikes, right? Those ones. There are reference to the frequency of the current, because we are just measuring the current. It's very interesting, but we have to be careful to know to identify these spikes and the spikes that we want. Then again, yeah, okay. And then on the overload, we have the similar. It's fun to see that in the both methods we can actually see some similar modes showing similar frequencies. So this concludes. There's work that needs to be done here. We can use the different features and combine them to analyze to detect the different events. And from the model analysis, a pre-processing needs to be done to get good results. Next steps is to validate these methodologies with experimental model analysis, where we know the excitation modes, and from that, have the operational model analysis. I just want to, one missing. Yep. Want to thank you to the project, and I think that's it. Thank you. Yeah.